Okay. So hi, everyone. It's good to see you all. Okay, so for this problem solving session, we're doing worksheet number 5 for the HoTT track. And let me first share my screen. Okay, so I think my screen sharing should be visible to everyone. Let me just make sure I have chat available too. Okay. Yeah. All right. So I have chat directly visible to me, so people can use that to chat or ask questions, and you can use audio to ask questions too. There aren't many of us here, so I think you guys can interrupt whenever you want, really. Okay. So, all right. So for this, so we're going to start with the first one. This is one I definitely want to go over. All right. So it asks us to look at a function f from a to b, and what we want to do is we want to construct a function that tells us that if f has a retraction, which is given as a definition here on the page, then basically it's injective, in the sense that if f of a equals f of a prime, then a equals a equals a prime. Okay, so for this, what's the first step when we want to construct a function like this? What's the very first thing we should do? So this function here, if I want to construct a function in type theory, I have to first do what? Yeah, so use a lambda. We're trying to construct a lambda expression. All right, so when we're constructing a general lambda expression, we need to assume, let's call it gamma, an element of the domain. So can we do anything more to help us out when constructing this particular lambda expression? Since if we look at the particular form of the domain, retraction of f. Yeah, right. So we can use, unpack the pair in the comments. So we can use sigma induction to assume, so the notation for judgmental equality is equals with a dot on top, I believe. So we can assume it has a particular form. Since retraction is a, actually I meant to write the form of the, of what retraction of f is. So this is a sigma type. It's the type of retractions of f. So we have a function b to a along with, as in the definition of retraction, a homotopy g composed with f is the same as the identity function. So going back to what we were just doing, we can take gamma to be a pair of this form, and I'll let R denote the homotopy. Okay, so this is a judgmental equality. Okay, so I'll use the 3 lines and the as synonymous with the equals with a dot on top, as in the book. So each of those denotes judgmental equality. Okay, so we have this particular form of gamma. So we know gammas of this form. We still have to construct an element of the codomain, this pi type. So, all right, I'll get us started there. We'll consider generic elements A prime of A, and we'll also consider a generic element of the identity type F of A equals F of A prime. Now what? What do we think? So okay, what do we have to do now? The codomain is a function. So we assumed A prime and P. We need an element of type. Oh, sorry. Of the identity type A equals A prime. So how can we start constructing an element of A equals A prime?
We compose with G?
When you say compose, so we have G. So we have G, and so when you say compose, we want to apply G to something, to some of the data we have, right?
Yes, we can see that we have F of A equal to F of A prime, and
Right.
we apply it to that equality type.
So apply G to this identity P, right?
Yes.
Okay, yeah. Right. So we have P, we have G, and then we can form the action of G on P. In the book and in HoTT in general, we denote this term by app sub G on P, which gives us a new identity. Okay. Okay, so, all right, yeah, great. So we have this new identity term, and we still need to show A equals A prime. How do we go from what we just got to A equals A prime?
The homotopy will give us equality types from GFA to A and GFA prime to A prime.
Yes. So we have a homotopy that states that G is a retraction of F, or left inverse of F, right? So this we have an identity, we have a term stating that this is equal to A, and that this is equal to A prime. Now, that's it, right? I mean, why is that it? So okay, let me so to be a little more precise, let me write it down here. We've shown that A equals, that we have a term stating that A is equal to G of F of A. And we already knew that this is G of F of A prime, and this is A prime. So Now, on the one on the right here, this is directly the homotopy, right? Stating that G is a retraction. Here, just to point out the proof relevance of HoTT, we took the term given to us by that homotopy up here, and we just applied the inverse of it, right? So that's how we got this one on the left. And then finally, path concatenation gives us a proof term that lets us actually state the transitivity that we're using at the bottom here. And finally, and that term itself will be the proof that A equals A prime, which is exactly what we needed to construct our function. Any questions on this first one? Okay. Just as a reminder, in that same GitHub repo, there is a solutions file. So in case anyone wants to look at solutions afterward to clarify some things, they are there. Okay. So cool. I wanted to go over the second one now, or at least not every single part of it, because there's a lot of similarities between the parts. So it might not be worth spending time on each and every one, but to get the idea, I want to start with the first one, the first part of the question too. So what is it? Okay, so let's consider the setup. We have a commutative triangle. So this is exactly what you'd see in non-type theory math that states that, so this is stating that we have a homotopy. G composed with H is homotopic to F. So the first question asks, suppose that we're given a section S of H, and we want to prove that, so prove, that we have a homotopy of this form, and also that we have a bi-implication stating that F has a section if and only if G has a section. So we need to give a function in each direction here. Okay. So let's start with this. Let's start with the first thing asked of us. Okay, so by implicate, question in the chat, what does by implication mean? I'm calling the symbol, the bi-directional arrow symbol here, a by implication, and unpacking it, it means that we have to prove a function in this direction, that if F has a section, then G has a section. And in addition, we have to prove that in the other direction, that if G has a section, then F has a section. So we're constructing a function in both ways. So this unpacks in type theory to a conjunction or a Cartesian product type. Okay. Now, this homotopy, F composed with F, is homotopic to G. So this means that for all B, sorry, my pen is a little funky right now. For all little b of type big B, we have an identity, right? Okay. So any ideas to build a term of this identity? We don't need to write out, it might be cumbersome to write out the exact proof terms, but since this is the informal track, what's the argument to get an identity of this type here?
You will apply you will look at there's that f is equal to a gh, and then you use homotopy from the section.
Okay, so yes, so okay, as I wrote up here, so as we had up here, we have a homotopy. So so f, if we, writing it in the other direction, f, as you were saying, is homotopic to G composed with H. So so yeah, let's start with that.
Is that an equality up there, or is an homotopy? Because we have a commutative triangle.
This is right. So it's not written out in the problem, but a commutative diagram, and here specifically a commutative triangle, denotes a homotopy, not an equality of functions for us at the moment.
Okay.
And this is a good time to remark that we're careful to use homotopies when we're talking about equality of functions so far in the book, because we don't have function extensionality quite yet. I know it was briefly introduced at the end of the last lecture, HoTT lecture, but without that, the things that we can do right now are a bit specific to using homotopy of functions. Okay, so yes, going back to this, f composed with S of B is G. Is G. Oh, that should be an H. So yes, we have this, and I think I might have missed the last. I think you might have said something from what we do at this point too.
That we use that S is a section
Right.
of H, so that's a homotopy to the identity.
Right. Remember, S being a section means exactly that. S is a right inverse of H, up to homotopy, of course. So this in turn will be G of B, and although since we're doing formal HoTT, often we'll leave it implicit, but this identity is applying G, is taking the action of G on the homotopy, stating that S is a section of H. So I'll just sorry, I didn't have the proof term ready, so I'll just be informal. S is a section of H. So I'm being very informal here, but okay. Cool. So yes, that gives us the homotopy we need. And then the second part says that we want a by implication that F has a section if and only if G has a section. So I think maybe in the interest of time, since each direction is somewhat similar, let's just do one direction. So in one direction, we need to construct a function that if F has a section, then so does so does G. Okay. So as you know, we're constructing a function. So let's start with the lambda expression. So we want to assume an element of sec of f, and this is the sigma type, stating that we have so f is a function of from a to x, so s will go from x, from x to a, stating that it's a right inverse. Up to homotopy. Okay. So we have, so by sigma induction again, so we could consider a pair, f s sub little f, and again we can let's see, let's call the proof that it's a section big K. I don't think I'm going to use the proof term here because we're being informal, but let's consider a pair of this sort, of this form. And we want to prove that G has a section. So what we need to do, as we saw from this sigma type, is actually give a function, a specific function that we'll need to prove is a right inverse of G. So what function do we want to use for that?
Just the composition, the s followed by h that goes from x to b.
You said s followed by h. Do you so okay, h is sorry. So h goes from A to B, and then when you say S, you might mean S.
The section of F.
Yeah. Okay. So I think what you're.
S of F. Sorry.
So are you? I think what
Yes.
you mean is, yeah. Okay. Great. So we have this composite H composed with the section of F. So that's what we are choosing as our candidate section of G. Let's actually prove, let's give a proof term, at least informally, that it is indeed a section, because that's the second element of the sigma type that we need for sec of G. Okay, so S, arbitrary element in the domain. So eventually we're going to need this equal to X. You know, we need this to be homotopy to the identity.
Because
so
the
yeah,
diagram commutes. So how would this say that? Because we have that the diagram commutes.
Yeah.
We have a homotopy between GH and F.
Yep.
But
yeah.
How do we say that formally? Because
sorry. Yeah. Keep going. I just got. Yeah. There we go. So how do we state
that we're using that property?
In how we're stating it here, as we're constructing the proof that it's a section.
Yeah, I don't know how to relate that, because I can say that we have the homotopy between GH and F, but I don't know how to write it formally in this language. Okay, yeah. So yeah, that's a good question. So part of the issue, I think, is that I didn't put a proof term. First of all, I didn't give a name to a proof that there is a homotopy witnessing this commuting triangle. So let's say
let's say I actually gave a name. Oh, sorry, G composed with H is F. So if I denote that as big H, then the way I would use it, for example, down here is, so I want to say that this is equal to F applied to S little f on X, and the witness to this would be
like something like H applied to SF.
Yes, exactly. Let me just make going back. Yeah, so H says that for all. Let me see if I can fit something in here. So I'll write it here. So H in particular, unpacking that term, for all little a of type big A, we have a, this is a proof that G of F, sorry, G of H of A is equal to F of A. So I think you had it, I think you were saying it correctly just before, that to get this identity here, that's exactly the term H applied to what?
SF.
Yes, and just to be precise, there's a little more. What exact H takes it? H takes in an element of big
Yes.
A, right? So, yep.
That will be SF in an arbitrary term of.
So, and I'm
X.
denoting my arbitrary term of the domain as little x, right? So, so okay. So this, yeah. So this is precisely a element of, and I already had it written out, but just to be extra clear, this is an element of the identity type that we wanted. Just, you know, just as we were plugging in an arbitrary element, just as here we were taking an arbitrary element of big A right here, we can just plug in S little f of X into it and getting a corresponding identity. Okay, so all right, so we have this identity, and then finally we do need this to, in order to prove it's a section, we need it to be homotopy to the identity. So we're going to need this to be equal to X. Is that true? And if so, why?
Can you repeat that question? Sorry.
Yeah, so finally we did get this term gives us the proof of that this right here is equal to that right there, f of S little f of X. But we need it to be, we finally need this to be equal to just X, so that this is homotopic to the identity.
Right.
Because we're choosing this to be the section.
And we use now the homotopy between F and SF and the identity type, and that's applied to this new the thing we have below, all the
Okay, so let's take that step by step. I think you were correct when you first said that to get from here to there, we can use the fact, we can apply the identity, the homotopy that states that S little f is a section of F. So this is the identity. And then informally speaking, that's kind of all we need for our proof. We could just end it there. I'm not sure, you might've said something else about the specific. Were you saying something more about applying this homotopy to this to get the identity here?
Because we have that homotopy and we just, so that's an homotopy that works on f of fs little f.
Yes.
And we have an identity type that relates to one of those terms.
Yeah. So again, unpacking a homotopy like this, we're saying that and I'm going to just leave this. Oops. So I'm leaving the elements in that S little f is being applied to and identity is being applied to blank, because we can put in any term of the right type here, right? We can put in any one of them, any element of the right type, and we'll get an identity of this form. So here, we're going to put in X because that's what we want down here. And that's exactly the identity we're looking for after we just noticed that this term on the right, identity function applied to X, is equal to X, right? And in fact, it's not just equal, it's judgmentally equal. Because you might remember that we defined identity function on a type as the lambda expression that takes in an element and outputs the same element. Okay, so great. So that proves that that indeed this right here is a section of G. The converse implication is pretty similar. So I'll leave that to you, or you can look it up in the solutions file. Let's see. What should we? Okay, let's see. What should we look at next? So yeah, I kind of wanted to skip 2 in the interest of time because it has a similar flavor to 1 that we just did. So I'll leave that to you guys as well. And I wanted to get to sort of the upshot of this problem, which is 3 and then finally 4. Okay, so let me say that we did part 1 here. And now I want to look at a bit of 3. And this also I won't be able to get to every part because, all right, let's see what it's asking. Prove that if any 2 of F, G, and H are equivalences, then so is the third one. So we have 3 choose 2 cases to consider. So that's 3 cases to consider. So I'm not going to go through each case, but to get the idea, let's do one of them. Okay, so does anyone? I don't have a particular preference to which one we do. Actually, I think in the interest of time, because I think maybe the shortest one is the case where, let's see, I think the slightly shortest one would be, suppose F and G are equivalences. Oops. This is getting messy. So are equivalences So we want to show that F is also an equivalence. So I think this could be a kind of short proof because we can make it kind of slick by using parts 1 and 2. We can minimize the amount of work we need to do. So any ideas or partial ideas on how we can start using our results from parts 1 and 2 to get that F is an equivalence here? First of all, let's recall, what do we need to exactly show to show that F is an equivalence? Our definition of equivalence is that it's bi-invertible, right? So this is the same as showing that F has both a section and retraction, or both a right inverse and a left inverse.
We can see that by one,
yep.
H has a right inverse. Means that F has a right inverse, and the second point means that if G has a left inverse, F also has a left inverse. No, sorry.
Yeah, okay, so let's unpack, I think, the 2 points you made. So let's start with part 1. Part 1 says that if so we want to work in the scenario that H has a section, but we do know that's the case here, right? Because we're assuming H is an equivalence. Yes. So we can apply part 1 to say that F has a section if and only if G has a section. And I think you were saying that, but we also know here that G has a section because it's an equivalence by assumption. So we can conclude that F has a section, correct?
Yes.
Okay.
And a similar thing happens when you assume 2.
Yeah, let's give me a chance to get a new page. Let me take a new page here. Okay. So by part 1, let me write this out. By part 1, since H and G have sections, we can conclude that F has a section as well. Okay, so that's one part of the data we need to prove that F is an equivalence. And I think you were also saying how we get the retraction as well by part 2, right?
Yeah, just by part 2, since we have that G and H have retractions.
Yep.
We conclude that F has a retraction.
Yes. By part 2, and I'll say likewise, this very similar reasoning gives us likewise, we see F has a retraction. Okay. All right. So yes, so F is now an equivalence. So I'll say as well. So those are the two components of F being an equivalence. All right, cool. So yeah, that's the slick proof for one out of the three cases for part 3. Since I want to get to some of the other problems, I'm going to leave the slightly longer cases to you or to look up on this in the solutions file. It's really not too much harder. You do need to do, each part requires you to do a new calculation, but you're also going to be applying the previous part to the exercise to get the result. All right, so I also want to do part 4 here because it's also pretty slick and it's a nice conclusion to this problem. Okay, so yeah, part 4 here. So it's asking us that to conclude that any retraction or section of an equivalence is itself an equivalence. Any ideas on how we can apply our previous results from this problem? And maybe as an extra hint, maybe we just need part 3 because that itself was kind of the upshot of parts 1 and 2 to get part 4 here.
We can get the commutative diagram.
Yes.
So if we have A and B and F a function.
Okay.
And
so
we get
F from A to B, sure.
Mm-hmm.
Yep.
And we get B to A, the section, for example.
Sure. So we have a section right inverse of F from B to A.
And we have the decomposition.
Yes.
So S of F.
Yeah. Okay. We have the composition stating that this is a section, right?
But we can arrange that in a commutative diagram, like A, B, and instead of X in the middle, we have A again.
Right. So let's write this as a commutative triangle. So so I have the two functions we just wrote, and so I think you were about to say it. What goes in the third?
The identity.
Error. Yeah.
Because we have the commutative diagrams up to MotoP,
yep.
It means we can plug the identity.
Yes, so exactly. This commuting triangle states exactly that S little f is a section of F. So this, remember that we already know this is a section. We're writing this down as a section of F because we're assuming that, oh yeah, I think I didn't write it down, but we're taking this to be an equivalence, right?
And I probably got the names incorrectly because I always confuse section and retraction. I think this is a retraction, but yeah, it's.
Oh yeah, sorry about that. Sorry. Yeah, that was my fault because I started writing it down. I wrote this triangle down in sort of a wrong way. All right.
No, I think that's just a retraction. Yes, I just said it wrong.
Okay. So in either case, to clarify, we're actually talking about the case. We're actually considering the retraction of F that we get from the fact it's an equivalence. And yes, so this commuting triangle at the bottom states that R is a left inverse of F. So we have this commuting triangle, and how can we apply part 3 to prove that little r of F is a equivalence?
Because the identity is an equivalence and
yes.
F is an equivalence.
Yes, so F and identity are equivalences. And applying part 3 lets us conclude that the retraction R of F is also an equivalence. Okay.
And for the section, we only exchange the place of the identity and the other function.
Yes. For a section,
think.
For a section, right, we're gonna, I'll write it. So we have the section. And then we have an identity here, right?
Yes.
So this is the section. Okay. And we can apply the same exact reasoning, right, to conclude that the section is an equivalence.
Right.
Okay. Yeah. Cool. Any questions on what we did in part, I mean, in question 2 here? Cool. So yeah, let's look at some of the other problems. Let me just make sure. Yeah, I think I did just, I think we can, I think we should still try to get through 3 and 4 because they're related problems. So let's try to get through them together here. All right. So question 3, we're considering the type of Booleans. It has 2 constructors stating that there's 2 canonical elements of bool, true and false. And I've given in the setup also the definition of a type family defined by double induction over bool. Here, it's as you'd expect, it's characterizing the equality type of bool, just like we did in lecture with the equality type of natural numbers. So we can call this observational equality of bool, maybe. So we have a proof that true equals true, no proof that true equals false, proof that false equals false, and no proof that false equals true. And then finally, the setup gives us for every 2 elements b and b prime of bool, we're defining a function phi b prime from the identity type b equals b prime to the observational equality type by path induction on b equals b prime here. And we want to prove that this function phi is an equivalence. Okay, so in particular, the approach we want to take is constructing a right inverse and a left inverse of phi, but it will suffice, and you might see already that we can, and this is often the case, especially in simple scenarios, that we can just try to construct a 2-sided inverse. And from lecture in the book, we might remember that it's actually logically equivalent that a function is bi-invertible and has a 2-sided inverse. Okay, but in any case, let's construct a 2-sided inverse of phi b prime. So let me go down here for question 3. So phi, let me write it as the candidate inverse as psi b prime. And this will go from equal b prime to the identity type.
Here,
so
yeah, go. Then this is something that I'm still trying to grasp. What type is the identity type below?
So this this is another notation for the identity type in bool of the 2 elements b prime, which are assumed to be elements of bool. Does that answer your question?
I'm just trying to understand if it where, how can I place that type in the universe, in U0?
Yes. Well, so you can do that by first noting that any universe, in particular U0, has a code for. Oh, I see. We didn't explicitly assume that it has a code for bool, but oh, I see. Okay, so going back up here, I wrote U0. So is this okay? Let me clarify. Are you asking how we can place this ek bool in U0, or are you asking how we can place the type bool in U0?
A bool and the identity types of bool.
Okay, so let's. So okay, that's a good question. You are right that in the definition from the book, we assume that our universes have codes for the base types, natural numbers, empty type, and unit type, but we didn't explicitly assume that it has a code for these new types that we can define, such as bool here, right, where we give constructors true and false. So I don't think it says it in the book, at least at this point, but we do allow our universes, we do allow ourselves to construct new types like this in universes, new inductive types in the universes, as long as they have a certain form. So we can construct new inductive types into our universes as long as the constructors have certain forms. You might see, if you read up on this stuff, that the form of these constructors have to be maybe strictly positive, which is a little out of scope for now. Okay. But we can get bool into the universe, into a universe by stipulating that we can construct new inductive types into it like that. And then once we have that, we know that universes are closed under identity types from the definition of a universe. So that's how we end up getting the identity type of bool like this in a universe.
Okay.
Okay. So what can we, how can we define psi, psi b prime of this type ek bool to b equals b prime?
It's pretty straightforward by case analysis on b and b prime, right?
Yeah.
If b and b prime are both true, then it's REFL true. If b and b prime are both false, it's REFL false. And if b and b prime are anything else, then the definition of EQ bool means we can use zero elimination. Yes,
great. Perfect. So let's start writing out some of the cases. So so we're gonna, again, we've been defining everything so far by double induction on bool. So if we want to construct an inverse to phi, we're probably going to want to do double induction on bool again so that we can use the computation rules given by the induction principle to actually prove that we have a two-sided inverse. So yeah, double induction on bool. Yeah, so a couple of the cases would be psi true is going to give us a function from the unit type to the identity type. And we can just map by induction on the unit type, we can map the canonical element star to REFL of true. Sorry, my pen is lagging quite a bit. Okay. And then as you were saying, let's take another case to get the idea. So this is so psi on, let's say, true, false. That gives us a function from the empty type into sorry, my pen is really true equals. Okay. And as you were saying, we can just use the elimination rule on the empty type. So if we have an arbitrary element of the empty type, we can map that to the function we get from induction. Okay, and similarly for the other two cases. Okay, cool. Yeah, so it's by double induction on bool again, it's pretty straightforward to check that psi and phi are in fact inverses of each other, that they compose to the identity function of the homotopy. Okay, so that's all I want to say for the solution of 3, but there's a note at the bottom of the solution. It says that it's easy to show that 1 is not equal to the empty type. Okay, so I'm gonna leave, and then as a consequence of that, we can prove the negation of B equals negation of B for any B in bool. So, okay, I want to unpack that a little bit. It's easy to show that it's not the case that 1 equals the empty type. You might remember, I think we've seen it briefly, that we can construct, let me go up here. If we have an identity, unit type equals empty type, then we can actually get an equivalence between unit type and empty type. And if we have an equivalence, then we can get an element of the empty type by applying the equivalence on the element of the unit type. And then once we have an element of the empty type, that's precisely what we want to prove the negation here, right? Okay, so we have that, so now I say that as a consequence, we can prove that it's not the case that B equals not bool. Sorry, B equals not B for all B. So by pattern matching on B, if we assume that, let's say, true equals not true, which by our definition of neg bool here, that'll be false. So if we assume true equals false, then we'd actually be able to get an equivalence between, let's say, this type here and this type down here. So the first one and the fourth one. And that'll, of course, if we get an equivalence like that, just as before, we'll be able to construct an element of the empty type. So that will prove this negation right here as well. Okay, so that's the idea of that comment at the end here of problem 3. And I wanted to say that because I do want to try to go over problem 4 here. Problem 4. Let me add page before. So problem 4 builds on this. And we can just do one of the four, one of the two things asked in problem 4 because they're very similar solutions. Let's do the first one. So problem 4. Let's prove that not is equivalent to the constant function at b. So b is any, little b is any element of bool. And to prove this negation, we're trying to construct a function from is equivalent constant function to the empty type. So let's do this. Let's say that we do have an equivalent, a proof. Let's say we do have a term, a function that is an equivalence. Let me rephrase that. So let it be the case that constant at b is an equivalence. So hiding under this is that we have a proof term that consists of a right inverse and a left inverse of constant at b. Okay, so how do we use that assumption to get a contradiction, an element of the empty type? And I'll give a hint. We may want to look all the way back at, it may be easy, or if we remember what problem 1 stated, which is that if a function has a retraction, then it's injective in this sense. Okay, so let's try to remember that as I go. Yeah, let me go back. So let's try to remember that. If a function has a retraction, then it is injective. So, and we've assumed that, sorry, this was poorly written. So we've assumed that, wow. So we've assumed that the constant function is an equivalence, and we want to use that if a function has a retraction or a left inverse, then it's injective. Any ideas on how we can put these things together? So, okay, I gave a hint that we want to apply problem 1, that if a function has a retraction, then it's injective. So what we want something that has a retraction. What has a retraction among our data here?
Const?
Yes, it's an equivalence, right? By assumption. So in particular, it has a retraction. So it has a retraction, so we can conclude that it's injective. Sorry, hopefully. And thus, okay, so it's injective. And so if const is injective, what can we do now?
Well, now you can say that that function, since const is a function f that takes true to b and also takes false to b.
Yeah.
From exercise 1, we can say that true equals false.
Yes. So, yeah, great. So, yeah. Sorry, this is very unfortunate that my pen has been so laggy. So we have that this constant function is actually definitionally equal to b, and that in turn is definitionally equal to const applied to false. Wow. Okay. So as you were saying, it's const b is injective, and therefore we can conclude that true equals false. Now, what's the final step here? And this is what, and as a hint, this is why I wanted to go over the last comment in the previous problem before we moved on.
But
Well,
we
so for
proved
true
that.
equals false, you can just get a value of the empty type from the previous work.
Yes, right. So we know that for any element of bool, b does not equal neg bool b. So in particular, true does not equal false.
False.
So that in particular gives us, we have true equals false and we have true not equal false. So that exactly gives us an element of the empty type, right? Which is what we wanted up here. Any questions on that reasoning?
Mm-hmm.
Okay. The other part of the problem is really the exact same idea. So I'll leave that to you guys. And then, okay, the last thing I wanted to get to, and I think, since there are still some people here and, I think it would be good to look at problem 5. That's the last one I did want to go over. Okay, so we have problem 5 here. And all right, what is it saying? We have a type family over A. So we can do the universe thing, or we could go back to just our original descriptions of type families as type expressions in a context like this. So either way. Okay, so we have a type family over A. For each X and Y in A, we want to construct first an inverse of the inverse path function, which takes a path and gives us a path in the other direction. So we want to construct an inverse to that function. And then secondly, we want to construct an inverse for each path from X to Y, an inverse of the transpose function. And this is a very important function in homotopy type theory. So I want to go over, I actually really, all right, let's go over both. It doesn't take too much time in either case, but transpose is very important. So I want to make sure we get to that too. Okay, cool. So let's look at the first one, constructing an inverse of this inverse function here. Any ideas?
Isn't this just one of the properties of the equality type, like the sim for the equality type is literally this function?
We have previously defined a function. This is already a constructed function, this inverse. We already have that. I want to and maybe this is confusing to put here, but I want to construct an inverse. And what I really mean is I think what we should be doing is constructing a two-sided inverse of this function here. And the function we're constructing an inverse to takes a path and gives us a path in the other direction. So we do have that from the identity type. But how can I construct a function in the other direction? It doesn't, maybe I misunderstood what you mean, but it doesn't, we don't automatically have a function in the other direction just by directly looking at the identity type. It's not just immediately given to us. We have to construct it.
We can't we use in X and Y, the Y and X, sorry, just changing. If we have it for any arbitrary X and Y, from understanding this incorrectly.
Yeah, no, yeah, you actually, I see what you're saying. Can we, maybe that's what, I forget who was saying it, might have been Ryan, but I think that might have been what you were saying. I just misunderstood.
Symmetry, I think.
Yeah, basically, the inverse we're going to be constructing, so let me write it down here. So this is problem 5. So, all right, let me just use a generic letter. So the map in the other direction for X, Y, you're saying that we're actually going to want to just take this to be the function given applied to Y, X, right?
Yes.
Yeah. So, yeah, you know what? All right. That's a good idea. Let's that's definitely one way to look at it. So let's go about trying to prove this. Let's do one direction. Let's start with one direction. To proving that these compose to the identity up to homotopy. And let me use Q, little q, as an arbitrary element of the identity type Y equals X. So I want to prove that for all X, Y, and Q, like this equals
Q, or the identity type in Q, right?
Yeah, up to homotopy, so Q, right? Okay, cool. Great, so we have this is an identity type. We want to construct a term of it, a term of this identity type for all X, Y, and Q. How can we do that? All right, to clarify, this is an element of the identity. So,
I'm sort of surprised we can, if we can.
Okay.
Like if inv is an arbitrary function, right? It might be one of these weird identity values that we haven't actually looked at real hard yet, other than some vague gesturing in the direction of the circle. In which case, composing it. I do
want to clarify that, just so the problem is clear. The function in INV here is actually it's not, it can't just be anything. It's actually a specific function we've already defined. It's the function that takes a path from X to Y and gives us the inverse path from Y to X. So that's important here. So this takes, so this, okay, so let's redefine it so that we all remember what we're dealing with here. The function in INV here was defined by path induction. So I'm taking the elements to be the same and then defining a type on REFL of X to be, by definition, equal to
REFL of X.
REFL. Sorry, did I interrupted you? Is this what you were going to say?
Yeah.
Okay. So this is, so sorry, maybe it should have said that in the problem setup, but this is the function we're dealing with. This function here defined by path induction like this. So, okay, so that's the specific function. And going back to up here, how can we construct an element of this identity type for any X, Y, Q? Do we have any, when we're constructing functions out of a type, in type theory, we often want to think, do we have any induction principle that we can make use of? Is there an induction principle of a specific type that we're dealing with that will be helpful? Do we have anything? Do we have any induction principles that might possibly be of use?
I'm too new to this, but in induction path or REFL of X seems to be.
So I think you said path induction,
inductions,
right?
Yeah.
Yeah.
Path
so induction on the identity type, otherwise, also known as path induction. So yeah, we can do that. We can assume X is exactly the same thing definitionally as Y, and that Q is definitionally equal to REFL of X or Y, right? I mean, they're X and Y here are definitionally equal at the moment. Oh yeah, so sorry, sometimes the dots on top don't show up, so I prefer the 3 lines. Okay, so yeah, we've assumed this now for path induction. So this here now reduces to showing in XX in XX on REFL X is equal to REFL X. Okay, so can we construct an element of this type, this new type here?
Yeah, that's just REFL.
Will be REFL of X.
Yes. So we know by our computation rules, by path induction from down here, that this term reduces to REFL X, and then again by the same computation rule that then this term applied to this reduces to REFL X, right? So we have to prove that REFL X equals REFL X. And as you guys were saying, that itself, so I'll just write it down here, conclusion we take REFL of REFL. And by path induction, that gives us the function we want. In REFL of REFL. And the other direction, proving that in the other direction, we have a composition, that the other direction composes with the identity is very similar. So I'll leave that to you. So, okay, the last thing I said, I really do want to cover the second part of this problem, because transpose is so important. So I want to also construct an inverse for transpose. And to remind you guys, this is a function from b of x to b of y. So let's now let's use psi for our possible inverse, two-sided inverse. That's how we're going to prove that. Oh yeah, it says in the problem statement, construct an inverse. That was supposed to mean two-sided inverse this whole time. So I guess I don't need to keep saying it. So let's construct an inverse psi from and okay, to be clear, psi will depend on p, little p, from b of y to b of x. So do people remember what how transpose was defined up here? How do we define for a p path in x equals y? Do people remember how we define transpose?
Path induction on x equals y,
Yep.
with the result being REFL of the function applied to x.
Okay, so yes, we did path induction x. So then we have to construct a term on REFL x. So that would be a function from b of x to b of x. And I don't know if you said this, but we took that function to be the identity function on b of x, right?
Yeah.
Right, so great. So that's the transpose. We're trying to construct an inverse. Any ideas on how to construct this psi?
Again, it seems like it's kind of the same thing. You do path induction exactly the same way, and you have the punchline be REFL in exactly the same way.
Yeah, great. So p is an arbitrary element of x equals y, which x and y are arbitrary elements themselves. So we're going to do path induction again. Path induction on x equals y. So that means we need to give an element on REFL x. So this will be a function from b of x to b of x. Cool. And as you're saying, just as before with transpose, we're going to take this to be the identity function on on b of x. Cool. So now we have our potential inverse to prove that the compose to the identity. So let me write out one direction. Transpose of b, of that itself is a p, and that'll be, let's say little b here. I think, do I have think that's enough parentheses. All right. Yeah, so okay, and B is a element of B of Y. Okay, cool. So we want to construct an element that this is just little b. And what would we do to get an element of this identity type? And let's think about how we define transpose and psi so that we can kind of easily get an element of the identity type down here.
Can we just directly apply those? No, we can't, because those are the things that we have written down in terms of psi and transport are, those are what get fed into path induction, right? So we have to apply path induction again here in order to like unpack them, I guess.
Yes, exactly. That's often what we're doing in HoTT is we've defined functions, you know, out of a type into another type by a specific induction principle, which gives us computation rules on the constructors of the domain type. And to prove that two functions defined in that way compose the identity, we often are going to want to do the induction principle again to take advantage of the computation rules that we obtained. So yes, you're exactly right. If we do path induction on little p again, then this reduces to what we defined here, and that'll be identity. Then this reduces to the identity. So overall, this whole expression will turn into identity of B, right? Which definitionally actually gives you back little b. So in particular, we do have an identity with little b here. Okay, any questions on that? And this was actually the last part I wanted to go over. So any questions on this or anything we've covered?
Not at the moment. That's still kind of strange language to get used to, as you were saying.
The last part I was saying with the path induction?
Yeah, like the thing that we're saying that often you go back and use the induction rules or the computation rules. Still kind of new, but yeah, it's been interesting.
Yeah, exactly. The main upshot, just to reiterate, the main upshot is we want to take advantage of the computation rules that we obtain by our induction. So in particular, we have a computation rule with the identity function here, and the transpose the same thing. We have a computation rule on REFL with the identity function. So that lets us, in this case, easily reduce this identity that we want to construct with an identity between identity of B and B, which comes out nicely because this itself, by definition of identity, is just B.
Mm-hmm. Thanks.
Right. Yep, sure. So any final questions, guys?
I've got a possibly too open-ended question.
Sure. I'm trying to, in the interest of that's fine. I'm happy to listen to it. I think just for the interest of keeping the video somewhat, in a reasonable length, the recording. I'm gonna stop the recording now, and then we'll continue chatting. Okay, so yeah, so thanks everyone for listening, and this is the end of the official recording. Wait, did I have been recording it. Sorry, let me just, yeah, it is recording. Why am I not? Oh, I think do I need to end share to stop recording? Let me do that. So let me stop share. Yes, now I can see. Okay, thanks everyone. Here's the end of the recording.